All right, everyone. Let's start with lecture 22, maybe? I'm not sure. Um, all right, so up to this point, you have been dealing with electrostatics, where the charges have been assumed to have arranged themselves in some sort of static configuration on a conductor or a capacitor or something along those lines. And we kind of saw that yesterday when someone asked a question about the delay between a battery trying to provide charge and a capacitor actually building up charge. And that's exactly right. If the capacitor started empty and was suddenly connected to a battery, those charges, there would be some time that the charges would then have to march forward, build up on the capacitor, similarly developing a accumulation of negative charge on the other end as the positive charges got pushed away into the battery. And once that charge builds up so that there is the same potential difference across the capacitor as the battery, in this case, it would become an electrostatic configuration. But building up to that point, there would be some sort of current, which we're going to use the letter I to signify current. In the case of a capacitor and a battery, this current actually would be a complicated function of time. And I think on Monday's lecture, you'll do RC circuits and will derive what that formula looks like for something like a capacitor hooked up to a resistor. But to at least get us started, let's try to think a little bit more about what electromagnetic current or electric current actually is and how it comes to be. So we're going to start very simple and qualitative and try to build up to something that's a little bit more quantitative. So current, if I were to try to find it, I might first think that it requires charge to move. You can imagine if I take some Q as my charge carrier, and the battery launches them, and they march their way along, that there's charges, be it positive charges or negative charges, depending on the material or depending on your convention that you're taking. Some sort of charge has to move. And I would say this gets us kind of the way there, but not fully, but not entirely the way there. Because there can be cases where charge is moving and you don't actually have anything that's representative of a current. Here's how we might look at it. Suppose you have a wire that is not hooked up to a battery or any sort of potential difference. And your Cyclops observer sets himself up along the wire and places a sensor along some cross section of the wire. And his entire task is to observe the charges that pass through the sensor. Now, if the wire is not hooked up to anything, there may be positive and negative charges that are free to roam around the wire. But they will be moving in essentially random directions. And then this random configuration, so the random motion of charge, you might expect that at any given point in time, there's going to be just as many positive charges moving past the sensor to the right or to the left as there is negative charges moving past the sensor to the right or to the left. So there's no current in this case. Similarly, you could have something even mechanical, like a water hose. Water hose moves water from one side of the hose to the other. So suppose this is the velocity of the water molecules. The water molecules themselves have a positive part and a negative part, the nucleus and the electrons. And so you might, in this case, it's not random motion, but there's bulk motion. Well, it's a motion of neutral flow. There's equal, plus, and minus charges. Moving past the sensor in the same direction. So again, I would say this is not an example of current. So you might imagine that in this case, what really needs to happen is we need to augment our definition here and say that there needs to be a net amount of charge moving, either through a wire, across a surface, something along those lines, in order for current to flow. So we say that current requires a net charge to be moving across a sensor from one part to another. And so let's try to be a little bit more quantitative. Again, here's your observer. They've set up a turnstile or something like that, that any charge that moves through has to pass through, and they clock the charge that is moving through. Suppose you have some net amount of positive charge moving from left to right across this sensor. We'll say consider a net amount of charge Q flowing past the sensor in some amount of time, delta t. So every second or every minute or however often you're measuring, there's a certain amount of charge you see passing by the sensor. We define the current past the sensor as the ratio of these two quantities. So let's define current as delta Q over delta T. The amount of current passing by in a given amount of time. As you might imagine, so nice I can now do calculus with you. That in the limit that we take these time measurements in smaller and smaller quantities, this just simply becomes the derivative dq dt. And this is how we define current. The units of current, just look by the equation, it's coulombs per second in SI units, which we define as the ampere, usually written as an A. Amps is another way you might see this. Named after Ampere himself, who studied current in great detail. A little bit of detail, we define current as the flow of positive charge. This is just a convention. So if we say the current is, say, 2 amps, that is signifying that there's 2 coulombs every second of positive charge moving in a particular direction. Now, it's not always the case that it's positive charge that is actually moving. You can have current that is not a positive charge. For example, in conducting metals, like copper wires, it's the electrons that are actually moving. But historical conventional reasons, we define the current as the flow of positive charge. Now, it's not to say it never happens. Ions in salt water, or electrolytes in salt water, rather. If you have a current going through salt water, it is positive ions that are flowing in salt water. In plasmas, you can have both serving as the current carriers. In stars, for example, which we treat as just a big ball of plasma, both electrons and ions serve as charge carriers, and currents can result from both of them. All right. So I will typically stick with the convention of saying that I will stick with the convention that current is representing the flow of positive charge, even though we're leading up to things like circuits, it will in reality actually be the electrons that are moving. So if this were class, I might do a think pair share. So I'm going to ask, I'll draw the picture and you can pause, and commit to an answer yourself. For the configurations I'm going to draw, is current flowing at all? If you plop down a sensor, would you measure a current flowing? And if you did, what direction would you measure it in? So in the case of A, and perhaps you have some conducting wire. You have a bunch of positive charges, and they are all moving to the right. And here's your sensor. So I think it's clear that yes, there is current flowing. We would say the current is pointing to the right in this case, the direction of positive charge. Oops. Suppose you have both positive and negative charges in equal numbers, and they're both flowing to the right. Is there a current flowing? This is similar to our water hose example up above. We would say no. There is no net current in this case. If I look at the positive charges, they have a current that is flowing. If I look at just the positive charges, they are moving to the right. If I look at the current associated with the negative charges, while the negative charges are moving to the left, we would signify that as since the negative charges are moving to the right, we would signify that as a current moving to the left. Again, define current as the direction of where positive charge is, or the opposite of where negative charge is flowing. So in that case, they cancel out. There is no net current. If you had just negative charges flowing to the right, I say, yes, there is a current, but it points to the left. Again, the current being the direction of positive charge or the opposite of where negative charge is flowing. Last case, suppose you have some sort of coaxial-like cable, and you have different kinds of charge flowing in different directions. You have positive charges moving to the right, you have negative charges moving to the left. Do you have a current? I would say the answer is yes, you do. So if I look at the current for the positive charges, they're moving to the right. And while the negative charges are moving to the left, that signifies a current that is moving to the right. So in this case, there is indeed a current moving towards the right in this case. All right, pretty straightforward. Now, when you actually set up a circuit, or suppose you have, suppose you have some battery that you hook up and then you have some sort of light bulb that you hook up here, which causes the light bulb to shine. In this case, the way I would draw this, I would say what's happening is that there's a current that is flowing, and taking the conventional assumption that it's positive charges that are flowing, even though for a wire it would actually be the opposite. That some current moves out of the battery, goes through the light bulb. Those electrons help light up the light bulb, and then those electrons march forward again, return to the battery. And we could specify that there is some current, which we give some arrow signifying the direction of the current through the wire. Now, when you set up a current like this in a very simple circuit, that really is just things that are using energy that's being deposited, onto the electrons via some battery. So I'm ignoring capacitors for now. Actually, I think I will likely ignore capacitors the rest of the week. So just batteries and what we will call resistors. This current is set up incredibly rapidly, and it reaches a steady state. So there's a steady flow of current that comes out of the battery, goes into whatever contraptions there are along the circuit, and then returns to the battery. And it's a bit of a misconception where in this case of what I've drawn here, that the current in this case is not only steady, it is constant everywhere. So it is constant before, after the battery, before it enters the light bulb, and it's the same steady current after the light bulb as the charge is returned to the battery. I think a big misconception is people have the idea that electrons get used up in certain apparatuses, like a light bulb, that electrons are being used up to make the light bulb shine. And if you think of this just in terms of a conservation, that can't be the case. If 10 electrons move out of the battery every time charge goes through the battery, if 10 electrons come out but only 5 electrons come in, every time a loop is made, you got 5 additional electrons that are being deposited onto the wire. And the light bulb itself is not destroying electrons, nor is it creating electrons. So the electrons that come out of the battery must match the number of electrons that go back into the battery. And so I like to think of charge carriers, be it electrons or positive charges or whatever, as just little. I imagine like a little electrons have a little backpack that the battery fills that backpack with energy capsules. The electrons march off, deposit that energy that they have in their backpack into whatever apparatus needs it, and then the electrons continue marching along. And then when they get back to the battery gives them some new energy and they start over again. Let's think a little bit, just to tease a more sophisticated version of what we think current might be and how current can be represented. You could ask, how much does measuring current depend on our Cyclops observer or our sensor? We had to put down a sensor in all of the wires we were drawing before. How much is our answer really a function of the sensor? So I could ask, in the case of steady current, which again I'm saying gets established very, very rapidly. How does the measured value of I depend on the sensor? So you might be able to think of it as, in this case here, suppose I have some wire that has some charge carrier. I'll draw as positive charges. They're all moving to the right. And I have sensor 1 over here. I have sensor 2 over here. And I have sensor 3 over here. Sensor 3 is at an angle. And this arrow represents the direction that the charges are moving in. Now, in the case of a steady current, again, since we know current at the more fundamental level is just individual charges moving around, my claim is that it does not matter which sensor you use. All of these sensors must measure the same current in a steady current case. If not, then you might be able to reason to yourself that this would, again, result in the buildup of charge, which would not actually be a steady state configuration. I've reached the end of the page, unfortunately. I am going to copy this. Here's the analogy I can think of it. In a steady current case, rather than thinking about current, think about traffic. So you got two intersections. And you have a sensor plopped down here, and you have a sensor plopped down here that are measuring the number of cars that are entering and leaving this particular street. And let's assume it's a one-way street that has no parking spots or something like that. So you can't. Let's call it a tunnel. So you can't just stop. If you enter the region, you have to eventually just keep moving forward and eventually come out. And you have cars that might be able to move in or out of the tunnel. And you can imagine if it were a steady state, then the number of cars that are entering this tunnel must match the number of cars that are leaving the tunnel. If not, if more were entering at sensor 1 than were leaving at sensor 2, the number of cars in the tunnel would build and build and build. Eventually, that would not be a steady situation. You would eventually have a pileup. Or similar, if there were more cars leaving at sensor 2 than entering at sensor 1, that would again not be a steady situation, because then ultimately, if you let enough time pass, the number of cars in that tunnel would decrease to 0, or to some very, very small number. So again, going back up to the case of current, the sensor 1 and sensor 2 I drew in the case of the cars, you can think of it very similar as this sensor and this sensor. But again, you can make the same argument for, say, sensor 2 and sensor 3. Because again, if there are more charges coming in where sensor 2 is than there are charges leaving where sensor 3 is, that is not going to be a steady situation. Eventually, there would be a buildup of charge in between those two sensors, which is not going to be representative of a steady state current. those charges would eventually start to change the amount of current that is flowing, which contradicts what we mean by steady state. Mathematically, you can think of a steady state as the derivative is zero. So di dt is zero would be an example of a steady state current. But you probably also clearly realize that sensor 3 looks very different compared to sensor 2. In fact, if this were a cross-section, you would argue that the cross-sectional area that charges can move through and get clocked for sensor 2 is smaller than it is for sensor 3. So the gate that is measuring how much charge is passing by for sensor 3 is larger than for sensor 2, yet I'm claiming that the same amount of charge is passing through each sensor. And you might be realizing that, well, in this case, they were moving at right angles to one another. In this case, they're moving at some different angle relative to one another. And for really just counting things that are passing by the sensor, thinking back to your discussions of electromagnetic field, you might say this kind of smells like flux. And that's exactly what this is. So rather than talking about the flux of an electric field, we're talking about the actual literal flux of charge carriers passing by a given location as a function of time. So we can try to write down now, to create a more microscopic view of what current is, we can actually try to write down how current results from the flux of charge carriers past a given cross-sectional area. And unsurprisingly, thinking back to your electric flux stuff from Gauss's law in electric fields, this is going to involve a simple dot product that takes into account if there is an angle between the cross-sectional area and the flow of, in this case, charge, that must be taken into account. So let's think about a microscopic view of current. So suppose you have free charges in a wire, say. And you want that charge to flow. You want to establish a current. You know how to make charges flow. To make charges move, you need to establish an electric field. In the wire. If there's an electric field, then charges will feel a force as a result of that electric field, and if we can choose the correct electric field, perhaps that allows the charges to flow. And that's exactly what happens. When you set up, when current is set up in a wire, what is really happening is that throughout that conductor, there is a net electric field that is set up that allows charge to flow in a particular direction. Suppose again, here's my wire. And I'm going to set up some electric field within this conducting wire. And it itself is filled with various charge carriers Q, which again, I will assume right now is positive. Now, if these are free charges that are just roaming around this wire, they are not just hanging out stationary, like a solid lattice or something like that. these charges, if they're free to roam around, have random motion, just like how the molecules of air in this room are flying around in random directions and colliding with each other. Um, or like how, or the example of random motion we looked at the beginning of this lecture. Each of these charges have some random motion that is associated with them. And for electrons in wires, this random motion actually is quite large, something on the order of 10 to the 6 meters per second. And you have a wire of charges of densely, which is incredibly densely packed with these free charge carriers. And so, like the air in the room, collisions are incredibly frequent, and that just kind of lets them all kind of randomly just bounce around with one another. Now, with an electric field, all that incredibly chaotic random motion is still happening, but on top of it all, there is a slight nudge. Every charge is feeling a slight nudge. In this case, if these are positive charges, they're feeling a slight nudge to the right. So while, if I draw an example of kind of two cases, suppose I have a charge Q that without an electric field kind of does this, it just kind of randomly moves. But in the case of an electric field, all those collisions tend to be very similar to one another, but there's a tendency in that case for overall, there is some tendency, a slight tendency for during all these frequent collisions that the charge carriers will start to move in a particular direction as a result of this overall electric field that they're feeling. So the E field establishes a drift velocity atop the random motion. And again, just to give you a sense of the relative values, the drift values for electrons in a wire is something like 10 to the minus 4 meters per second. This drift is the current. Which resulted because of an electromagnetic field that was established in the wire. Note at this point, I have not really said where that electric field came from. That will come later. For now, let's take it as a given. This slight, very slight drift atop the random motion is the current. And you can see just by comparing the values, 10 to the 6 versus 10 to the minus 4, electrons are not whizzing around circuits and incredibly quickly. They are not flying around at 1% the speed of light across the circuit. In this case, electrons are just gently nudging themselves, along a circuit. But, as the electrons nudge and kind of drift slowly, some of that drift then goes through devices like resistors, light bulbs, whatever, and energy can be deposited as a result. Okay. So let's try to be a little bit more quantitative. Then how does current relate to this drift velocity? Okay, so let's draw a cylindrical tube, and suppose it is filled with some charge carrier, which again I'll take as a positive. So each of these is some charge Q. And they have some drift velocity, Vd, which I'll write as a vector. since velocity is in vector. And I'm measuring current, I'm setting up my turnstile here where I'm counting the charges that pass through this sensor, and I want to measure current and ideally relate current to some of these more physical properties like drift velocity, charge, etc. Now looking at this in terms of each individual charge carrier would be a nightmare. We could do it, but let's not. So let's make a couple assumptions, kind of similar to what we were doing when we did thermodynamics back in Physics 1. Let's, just for pedagogical reasons, we'll assume all these charge carriers are the same charge, have the same charge Q. And have the same drift velocity Vd. That's actually a pretty good assumption. And then on top of this drift velocity, of course, they all have their individual random motions. But again, the random motions are not what create the current. It's the slight drift atop the random motions that matter. When you're dealing with something like this, where you want to think more statistically, do a statistical average compared to looking at individual particles. Rather than looking at individual particles, we can instead talk about the density of these, in this case, charge carriers. So this is exactly what you would do in, say, a thermodynamics or a fluid dynamics course. Rather than talking about individual particles, we'll talk about the density of these objects. So we'll assume there's some number density n sub q. This is a number density. So the units are kind of number of charge carriers per volume. Similar where mass density might be grams per meters cubed. This is just number per meters cubed or centimeters cubed or whatever. So you have some density that gives you a sense of the number of charge carriers in a given volume. In a time delta t, how many charge carriers pass by the sensor? Again, we're looking for a delta Q. If we know a delta Q and a delta T, that gives us current. So again, since we are talking about flux, we're thinking about what is, another way of phrasing this is what is the flux of particles through the sensor? If the sensor has some cross-sectional area A, and since it's a cross-sectional area, I've written it as a vector. So there's some normal vector that is associated with it that points perpendicular to the surface. And I want to look at the flux of stuff that is going through that sensor. Unsurprisingly, that is going to depend on the direction and magnitude of the drift velocity. But it should also depend on things like how many charge carriers there are. If it's a densely compact container of charge carriers, more charges are going to pass by that sensor every second compared to if you had a very, very diffuse, nearly a vacuum of charge. Then while there might still be charge moving through that sensor, fewer are going to actually be passed by and logged in a given amount of time. So going back up to this diagram, we can think about if I had to shade in the volume that corresponds to the region that will pass by the sensor. If I just started the clock and let all these charges start to drift, they would all start to drift their way to the right. The charges that are immediately at the sensor would immediately pass by the sensor and get logged. This, for example, might be immediately logged as soon as I start the clock. And then once those are passed through and a little bit of time later, then these might get logged, then these, etc., until a given amount of time delta t has passed. So we could relate how much of a volume passes by the sensor. I can write some distance, the distance that all of these charges travel in a given amount of time delta t is just going to be the velocity times delta t. And so I'll shade that in green, where I can imagine this region here might be the region where, again, this is kind of at some length delta x. That is the region that in a given amount of time delta t, all of those charges that are in that little cylinder will pass by the sensor and get tagged. And their question now is, what exactly is that delta Q? How much charge is in this little green cylinder I've drawn? Well, that cylindrical shape, which I keep saying cylinder just because that's the way I've drawn it, but it could be any arbitrary shape. The number of charges in that volume that I've drawn in green is just going to be the density of charge so that's charge per volume times the volume of that region. So in this case, this is the volume of that green cylindrical region. In this case, that is nothing more than the charge density, and then that volume, if you just look up at the diagram, it's going to be delta x dotted with the cross-sectional area. If it's a cylinder, the area might be pi r squared, where r is the radius of the wire. If it's a different shape, it would be some different configuration that you use. But we just argued that delta x is just delta t times velocity, the drift velocity in particular. So I might write it like this. And again, taking the dot product, because you have these two vectors, mathematically you could think I need to take some sort of thing that turns vectors into scalars because the number of charges, capital N sub q, is a scalar. But the dot product, again, is also taking into account the flux. It is taking into account the fact that if the velocity is, say, perpendicular to the cross-sectional area, then obviously nothing is passing by the sensor. And that is maximized when the velocity is perpendicular. Sorry, I think I said that backwards. If the velocity is parallel to the sensor, then obviously nothing is passing through the sensor. Or I think this is what I meant. If the velocity vector is perpendicular to the normal vector of the cross-sectional area. And then obviously this is maximized when the velocity vector is parallel to the normal vector of the cross-sectional area, or the velocity itself is perpendicular to the cross-sectional area itself, since the dot product introduces that cosine factor. All right, so this is the number of charges that pass by in a given second. The next step is to then turn that into a delta Q, which is then just the amount, the charge per charge carrier times the number of charges that pass by in that given amount of time. So then this is just Q N sub Q delta T, drift velocity times the dotted into the cross-sectional area. Then going forward, delta Q over delta T, which is the current, then just Q N sub Q VD dotted with A. Now you might say, who cares? We can give some names to these things. The current, delta Q, is a function of time. We just wrote as the charge carrier density times the drift velocity dotted with the cross-sectional area. This thing here, which depends only on kind of the microscopic properties, is called the current density. And usually is written as capital J. since the drift velocity itself is a vector, the current density itself is written as a vector. And so sometimes you'll see this written as just J dot A. Actually, in general, in this case, I had a fixed cross-sectional area, and we made a couple assumptions. Really, by stating that the charge density was a constant throughout the entire tube that was drawn above. I did not have to consider that there might be different amounts of charge going through different parts of this cross-sectional sensor area A. So in general, we just say that rather than I is just J dot A, the more general version is I is J dot dA. Then units of J, you can see is just current per area. So amps per meters squared or something. Now this is useful because this is connecting something more macroscopic, like the overall current, with what is going on at the microscopic level. You have charges Q that are distributed with some density and are drifting because of some electric field at some velocity, and that is the result of what is creating the current as it goes through your given sensor, whatever that is. And you could even try to work it out for yourself. You might make an approximation of a cylindrical wire and use the 3 sensors that I used above. 2 were vertical and 1 was at an angle, and maybe estimate that angle is 30 degrees, and you can show that this dot product would give you the same value of current in each case. All right, so I think there's only one more thing I want to say, and then we'll call it a day. Let me just motivate what's coming. We already talked about is what's driving this current, this drift velocity. The charge carrier is moving through the wire or the conductor or whatever it is the result of some sort of electric field. And we haven't really said where this electric field is coming from, but I will try to kind of sketch an idea of where it might come from in the case of a capacitor hooked up to some wires. So suppose I have a capacitor that is currently charged up. So there's lots of positive charge on one end, lots of negative charge on the other end. And each plate is connected to 2 conducting wires that they themselves are not connected. Currently there's a switch that keeps them not touching from one another. And so as a result, what happens, in electrostatic configurations that some of the charges will distribute themselves kind of more or less uniformly throughout the wire to establish while there is a non-zero electric field kind of in between the plates, this is set up so that there is essentially no electric field along the wires. The charges will distribute themselves up so that they're in some sort of electrostatic configuration, and from your stuff with Gauss's law and conductors that the electric field inside the conductor must then be 0. So there's a nice balance that prevents the charges from roaming around. But in this case of the capacitor, there would likely be a strong electromagnetic field or electric field in between the plates. And you might say at this point, like, okay, yes, that makes sense, but if the electric field is 0 inside the wire, why would charge move at all? We just said that charges have to move as a result. Where is this electric field coming from? So now let's let's copy this. Now let's drop the switch and actually connect the two together. Notice in this case, the symmetry really has been lost, particularly at this point, at this junction here. Originally, right before the switch was dropped, the electric fields on both ends of the blue and the red ends were situated so that there was no tendency for the positives to move in any direction, or for the negatives to move in any direction. But now when the switch is dropped, in this case, there's now this new path that can be taken. The positive charges are going to feel inclined to want to move towards the negative charges. The negative charges are going to feel inclined to move towards the left, towards the positive charges. And so that lack of symmetry initially creates a non-zero electric field, in this little switch region, and as a result, the electric charge starts to want to roam across the switch. But then, as you might be able to imagine, before all the charges were set up in a nice electrostatic configuration, but as the charges begin to move, that symmetry, whatever symmetry had been set up originally, now is being broken. And so as a result, there is an overall net electric field. In this case, if I had to draw it, it would kind of look like this. That would drive positive current over to the right side and drive the negative current over to the left side if they both were free to move. If this were, say, a conducting copper wire, then we know it would just be the electrons, the negative charges that would move to fill in the voids that left a positive kind of charge left over on the left side. Now again, this all is happening literally in a nanosecond. This kind of redistribution happens very, very quickly, and so the electric field itself is set up very fast, which allows the current to start to drift. But again, remember the drift velocity itself is incredibly small, and as a result, it's not like charges are flying over to one side or the other, but there are slight shifts that allow the charge distribution to change. That electric field, given the electric field, that establishes some sort of current density on the wire, which then allows current to flow. And you might ask, how does this current density depend on the electric field that is set up? And that is tomorrow's lecture. All right, I think that is it for lecture 1. I will post this, and please, hopefully if you are hearing this, you are listening to this the day before we actually do some problems involving current density. All right, see you soon.